We're on page 36 and we're going to work out a couple of examples about energy conversions. Number 1. A tourist drops his camera from the Leaning Tower of Pisa, which is 45 meters high. A. Calculate the velocity with which the camera hits the ground. As soon as we read the question, we don't really have enough information to figure out the velocity. However, when we dig a little bit deeper, we see that we were given the height. Now you might tell me, but in order to figure out either the KE or the GPE, we still need the mass, but that is not really necessary. Let's see how this is worked out. So to start off, from the principle of conservation of energy, we get KE equals GPE. Kinetic energy is equal to gravitational potential energy. The gravitational potential energy at the top will be equal to the KE at the bottom. And since we said that energy cannot be created nor destroyed, then all of the GPE at the top will turn into KE at the bottom. Therefore, we can go to KE equals GPE. Now, if we put in the equations for these, we get 1/2 times m times v squared. Let me remind you, this symbol over here represents to the power of. You don't have to write it, you can simply write the 2 as we usually do, small and above. 1/2 times m times v squared is equal to mgh. Now, since we have m on both sides, that means they cancel out. So the m here cancels out with the m on the other side, which will leave us with 1/2 times v squared will be equal to g times h. Now, as we said last time, multiplying by 1/2 is the same as dividing by 2. So if we are multiplying by 1/2 here, and we're going to take it over to the other side, then instead of dividing by 2, we're going to get a multiplication by 2. So that will give us v squared is equal to 2 times g times h. Finally, if we wanted to get rid of the squared of the v squared, we have to square root all of 2 times g times h, which will give us v is equal to the square root of 2 times g times h. If we put in the values, we will get v is equal to the square root of 2 times 10 times 45, which we can write as v equals the square root of 900, and the square root of 900 is 30. And the units are meters per second. So the velocity with which the camera hits the ground is 30 meters per second. As you can see, we found the final velocity without having much information. All we knew is that the tower is 45 meters high and that gravity is 10, because we always take gravity to be 10. Question B. State what happens to the kinetic energy when the camera hits the ground. Now, as you can imagine, if we were to drop something from 45 meters of height, which is about 15 stories, as you can imagine, as soon as the camera hits the ground, it's going to break into a lot of pieces, 1,000 pieces. What will happen is that the kinetic energy with which it hits the ground is going to turn into sound energy, definitely, because as soon as the camera hits the ground, we would hear a crash or parts cracking, and as soon as the camera hits the ground and breaks, each individual piece that breaks off is going to fly away in a different direction. So there we have the kinetic energy is going to change into sound energy as the camera breaks, and the kinetic energy of the individual pieces that are breaking off. Question 2. A hammer of mass 1.4 kilograms falls from a crane 120 meters high. A. Calculate the potential energy gained by the hammer before it falls. So, this is simple. All we have to do is find out the gravitational potential energy. To do this, we're going to use the equation, which is GPE equals mgh, plugging in the values that we have. So 1.4 kilograms for the mass, and the height is 120 meters. The gravity we know is 10. Putting in the values, we will get GPE equals 1.4 times 10 times 120, And when we work that out, we will get 1680 joules. Question 2b. What is the velocity of the hammer just before it touches the ground? Now once again, here we have to use the principle of conservation of energy, meaning that we're going to start off by stating that the kinetic energy is going to be equal to the gravitational potential energy. So Ke equals GPE. Now this time we've already found the GPE from the previous questions, which is 1680. So we can substitute 1680 for GPE and the normal equation for Ke, which will give us 1/2 times m times v squared, which is the equation of Ke, is equal to 1680, the answer from before. Here we have to find the velocity of the hammer. So once again we have to get the velocity subject of the formula, meaning that we have to take the m over to the other side. Since it is a multiplication here, it's going to become a division on the other side, and instead of dividing by 2 that we have here, it's going to be a multiplication by 2. This will give us v squared is equal to 2 times 1680 divided by m. Now to get rid of the power of 2, once again we have to find the square root of all of this term, which means it will give us v equals the square root of 2 times 1680 divided by 1.4. Once again, I have to remind you of the importance of writing the 2 times 1680 in brackets. Even though in this case, if you were to just enter into your calculator 2 times 1680 division by 1.4, it will still be correct. However, it will be better for you if you get used to writing terms in brackets. Now the answer for all of this will be 49 meters per second. Question 3. Robin Hood exerts an average force of 100 newtons in pulling back his bow by 0.5 meters. He fires the arrow of mass 0.2 kilograms vertically upwards. A. Calculate how much energy is stored in the bow before it is released. Now in this case, in order to figure out how much energy is being stored in the bow, we have to remember another equation that we learned, which is that work is equal to the force multiplied by the distance. The force we know is 100, the distance we know is 0.5. So to start off, we're going to find the work done by Robin Hood in this case to pull the bow backwards. So starting from the equation, W equals Fs, we can simply replace F and S with the 100 newtons and 0.5 meters respectively. That will give us work is going to be equal to 100 times 0.5, the answer of which will be 50 joules of energy. Let me remind you that we've answered this question, we've chosen this equation because we were asked to figure out how much energy is stored in the bow. And as we had said in page 35, when he has pulled the arrow backwards, he is doing work against the tensile force of the bow to store energy as elastic potential energy in this case. Moving on to page 37, how high does the arrow go when it is fired? Now let me remind you, we were told that Robin Hood shot the arrow vertically upwards. So we can figure out how high the arrow goes by getting the height from the equation of gravitational potential energy. So starting off from the equation, we had said that the work done is equal to the GPE. Now we've already found the work done to be 50 joules in the previous question, and we know that the equation for GPE is mgh. So we can rewrite all of this as 50 is equal to the mass times the gravity times the height. Now, since we want to know how high the arrow goes, we have to get h to be subject of the formula and get rid of m and g by taking them over to the other side. And since these are multiplication over here, as soon as they go over to the other side, they will become division. So we can rewrite this equation as 50 divided by m times g is going to give us h. Once again, let me remind you to place m and g in a bracket. Putting in the values that we know, we get h equals 50 divided by 0.2 multiplied by 10, all of which will give us an answer of 25 meters. That is how high the arrow goes when it is fired vertically upwards. Question C. Why would the actual height reached by the arrow in real life be slightly less than the value calculated? The reason here is that whenever we do these calculations, we always assume that energy is being transferred into only the energy that the question is telling us. For example, in this question, we are assuming that all of the work done is being changed only into gravitational potential energy. However, we know that in real life, there might be other sources of energy that the work done in this case is being changed into. Generally, heat and sound. So in the calculations, we are assuming that there are no energy losses and all energy is being converted into the desired form of energy, which is not the case in real life. Question 4. A soldier uses his rifle to shoot a bullet of mass 20 grams upwards. The chemical energy stored in the gunpowder is 150 joules. So straight away, as soon as we read the question, there is something that should grab our attention. That 20 grams is not a value that we can work with. We have to convert that into kilograms, which will be 0.2 kilograms. Question A. If 30% of the chemical energy is converted to potential energy, calculate how much potential energy the bullet gains when fired. Now, this question has nothing to do as such with the equations we are learning or with the principles we are learning. It is simply mathematics. If you were told that the gunpowder has 150 joules, of which only 30% become potential energy, all we have to do is find 30% of 150. To do that, all we have to do is 150 multiplied by 30 divided by 100, which will give us an answer of 45 joules. So 30% of 150 is only 45 joules. Let's move on to question 4b. What are the two other types of energy formed after the bullet is fired? So in question A, we were told that some of the energy turns into potential energy. So we cannot mention PE again, because we were told two other types of energy. So definitely, whenever you're going to shoot a bullet, the bullet is going to fly away, it's going to move. So if it is going to move, we definitely have kinetic energy. Whenever there is an explosion, we will definitely have heat energy. And generally speaking, whenever a gun is fired, there is also a lot of sound. So if you were to write down two of any of the three I mentioned, that would be a perfect answer. Kinetic energy, heat energy, and sound energy are other forms of energy that we get whenever a bullet is fired. Question C. Calculate the maximum height that the bullet can reach. To find the answer here, we need to refer to the equation of potential energy. So we start off with gravitational potential energy is equal to mgh. Now we've already found the GPE to be 45 joules from question A. We know the mass of the bullet to be 0.2, which we were told in the original question. And we know G to be 10. So all we have to find is H. So substituting the values for what we have here, we get 45 is equal to 0.2 multiplied by 10 multiplied by H. But we need to get H subject of the formula. So we need to take the 0.2 and the 10 over to the other side, which means they will go from being multiplications to being divisions. So if we rewrite this equation, we can get 45 division by brackets 0.2 times 10, close brackets, which will be equal to the height. When we work that out, we will get H is equal to 22.5 meters. That is the maximum height the bullet will reach. Finally, question 5. A car of mass 600 kilograms is traveling at 20 meters per second. A. Calculate the kinetic energy of the car. All we have to do is refer to the equation for kinetic energy, which is Ke equals 1/2 mv squared. From the information we were given, mass is 600 kilograms, the velocity is 20 meters per second, so all we have to do is substitute those values into the equation, which will give us Ke is going to be equal to 1/2 times 600 times 20 squared. We can rewrite that to be 1/2 times 600 times 400, the answer of which will be 120,000 joules. Here, as you might have already realized, there are too many zeros, so I have to convert that value into standard form, which will be 1.2 times 10 to the power of 5 joules. Moving on to page 38. How would this value change if the mass of the car was higher? Now again, if we start off from the equation, which we know is 1/2 mv squared, if we were to increase the value of the mass, then the value of the kinetic energy will also increase. B2, the velocity increased. Again, if we start from the equation Ke equals 1/2 mv squared, if we were to increase the velocity, Ke will not only increase, but since Ke is equal to 1/2 mv squared, so if we change v, then Ke will increase even more. Question C. What happens to this energy when the brakes are applied? As we had previously said, whenever you press the brakes, you are going to turn all of that kinetic energy into heat, because as you press the brake, friction is going to be created within the braking system, and the kinetic energy will be converted into heat. You might also get a bit of sound if the brakes are not particularly new and they start squealing. So it is turned into heat in the brakes and sound if they squeal.